Hello developers, let's start developing. So tonight we're gonna continue with the task 17 of the 2024 Advent of Code. I had some work to do actually, but in between I was kind of thinking about this task. It was annoying me, but in a good way. So I am Veko and we're gonna emulate some stuff. So I started by looking at the program itself. It goes like this. I analyzed, so we're not gonna concern ourselves with the demo program, which is unrelated kind of to this, somewhat. But let's take a look at this program that we have. This is the program that we have, and these are the actual values that we want to do, and this is the actual program. So it literally says move A modulo 8 to B, XOR B and 5 into B, divide A with 2 to the B, then store it to C, then XOR B and C into B, then XOR the new value of B and 6 into B, divide A with 8 and store it in A. Print B in while A is not 0, do the same thing again. So I did a bit of analysis and came up with some insights. So first thing is that we're only storing something in A on this line, and we're only comparing it that. So it doesn't matter what we start with. If we have a certain octal representation of A, which means, or let's have it as a binary, if it says something like this, in each run, let's have it like this so it's kind of textual. In each run, we are dividing it by 8. And in binary, that means that we are removing the last 3 digits. So this becomes shorter and shorter and shorter and shorter and shorter and shorter and shorter until it's left with a 0. So we know what the value will, that it will eventually terminate. But on the other hand, we can guess at the length of the input. So if it's between 1 and, if it's between 0 and 7, the length of the input will be 1. If it's between 7 and 8 squared, 63, that's the biggest 2-digit octal number, I would say. That's 77 in octal. It's gonna be 63 and 3 digits and so on and so forth. So this is 8 times 8 minus 1, and then we will have 8 times 8 times 8 minus 1, so 511. Between 64 and 511, the length of the output will be exactly 3. That's something that we can know. So that means that the length of the input and our length of the output is 16. We're going to have between this number and this number. So anything above this number will have 17. Anything below this number will actually have, we can use this thing actually, since it's going to be even. This is 8. Between this number and this number is going to have exactly 16 letters in the output. That's good, but which means that if we run an exhaustive search of this many cycles, and that's millions, billions, trillions, so that means that we have 246 possible candidates. 246 trillion possible candidates. That's weird. But then I noticed something else, that each time that we start this code, we are setting this value into B. So the remainder of I divided with 8, the last octal digit of A goes to B, and thus resets it. So it doesn't matter what we have before in B, B is gone and we are pushing in a new value. And the same thing happens with C on this line. So here we're doing something with B. So whatever happens, the values of B and C in each cycle are reset. So they're only dependent on A, which means we don't have a bleed through, so to say, between cycles. And this is extremely important because, for example, if we have a 3-digit A, I'm gonna work in octal. So if something is 1, 2, 3 in octal, after the first loop, we will remove, since we will divide A with 8, we will have some output that's X. And we will have 12. And then 12 will have an output of Y. And then 1 which will have an output of Z. For the X, the whole 1, 2, 3 is important. But after that, anything that happens is the 3 doesn't affect it. Which means that if we have a number X, which has an output of something, imagine commas between something, and then we have the number 8x plus whatever, when whatever is another octal digit, this will be question mark something. We will have an extra output, which means that if we can get the back part of the output and extend it, we can do that. So we can now kind of solve this thing manually. And actually, let's do that, because I'm still not totally sure how to do that. So basically, what we want to do, this 0 will only and only be affected by the first decimal digit in first octal digit in our input. So that means that we only need to loop through anything that has an octal digit through all the octal digits. We can do that quite easily. Let's open this. So I will say run from 0 to 8 and literally give me all the values. We don't need that, we don't need that, we just need to run from 0 through 8. And note that we're looking for the smallest one. So we're looking for whatever gives us the first 0. Value 3 failed with a 0, and that's the only one that produced 0. Great. So anything that starts with 3 octal, let's see if I have a calculator that supports octal. That should be programmer. Yeah, it has octal. So anything 3, 5, 6, 7, 1000, 1911. So let's see, let's check that. So if we have 1911 up to 1912, if my theory is correct, this should have an output of 4 letters ending in 0. Yup. 1030. So a 4-digit octal number results in a 4-digit response. It's a weird mapping, since there's a lot of XORs, and XORs are totally weird to debug, so we're not gonna do that, but we can take a note of that the last digit will be 3. Actually, the first digit will be 3. And now we need to find the second digit. So we can say run from, can we use this octal numbers? Yeah, we need to do this. JavaScript fortunately supports octal literals. So I will say an octal literal from 30 to 37. So we are now looking for the one that results in a 3. The first one that results in a 3. So those values are actually this one. So we have 3, 0. We got it initially. Note that all of them have a 0 as the last part, because all of them have a 3 as the first digit. So we will take this thing, 3, 0. Let's continue. So we can now say 300 to 307, and the thing that we're looking for is 5, the first 5. Note that there are multiple 3's here, but we are only interested in the first one, and that one is also 0. Great, so 300 so far, and move on to the next digit. 000 007. The number that we're looking for is once more 5. Let's see. So we need to find 5530. 5530. The first one is on the 2, 012. So the next number is 3002. Let's continue. Three thousand and two, 7. Yeah, the input still stays the same. We're not gonna break it. And we're looking for, we didn't know what we're looking for, something, and you can see all of them end on 5530, but we want to end on 35530. And that's yet another 0. Great, we have that. Continuing on. This is a 0, enter a 0 here, and this is getting unwieldy. Oh, and it's gonna get unwieldier. What are we looking for? We're looking for 0. And we're getting a 0 on the 2. Great, another 2. Going back to the code, this time we're looking for 6, 2, 2. And I kind of get the feel why people like computers, because, ooh, because this thing doesn't work now. We got to a stage when none of the 7 options actually provided us with a 6, which means that we're gonna need to do some backtracking. So yeah, we were looking for the smallest one, but here we had only 1 0, here we had multiple 3's. So now I will need to check this 3 and then this 3 and so on and so forth. And I kind of feel that I would like to automate this process. Let's try that. So some typing later, we're back, and I summon the power of recursion. what we're doing here, we're calling this method find quine value, because this is a quine, a program that outputs its own source. And I'm gonna have the targets as the variable part, and then 0 as the starting position, because that we have. So now, in each run, if we run out of targets, that means that our candidate is actually a solution. Otherwise, we're going to take the last number. So in our case, we're taking the 0, and we're continuing onward. We're starting with all 8 numbers that are possible candidates from 0 to 7 octal, and we're going to construct our new candidate. So the new candidate is the old candidate, we're pushing it and adding a new digit. If this was decimal, we would do it multiply by 10 and add a digit. Since it's octal, we're multiplying by 8 and adding a digit. And then we're going to run that program on our computer. Now, we know that everything after the first output character is already matched. So we're saying, if the first character is matched, then we're going to do a fan out, basically, and run this analysis for all options, because we might have multiple options, so to say. So, and if then we're going to call and recurse and try to find a quine value if on that result, if it exists. If it doesn't exist, if this loop runs through and this doesn't execute, like we got with the 6 when we were looking for, we will never get to this. So we're going to return 0. So if the result is 0, this didn't pan out, otherwise we found something for that target. And return it. So when I run this code, this is what I get. So we found a candidate for the 0, for the 16 length target. This was one option. Target 15, target 14, target 13, 12, 11, and here we backtracked. We're going back to 12, back to 11, going up to back to 12, up to 11, 10, 9, 8, back to 9. 6, back to 7, 3, back to 7, since that didn't pan out. And then we got for 2, and it seems that we found this thing. And this is the actual input that we have. So this looks like a number. Let's see how it looks in the octal. Oh. Display, oh, we were correct, 3002, and then we have 511, 3532. This is the actual 16 octal digits that we were looking for. But then decimal representation is this. So let's see if this is our actual correct value. I have no idea. I really hope so. Let's see. And that's the right answer. Fortunately, we are returning on the first item that we find that fits our objective. So there might be more solutions to this, but we don't care, since we were looking for the lowest possible one, which is this tiny 16-digit number. Well, is it 16 digits? It's 16 digit in it's 16 digit in octal, but is it 60? How many digits does it have in decimal? Let's say, oh, it's 15 digit only. If we format it like a number with 1,000 separators, yeah, it just 105 trillions. So we were actually quite lucky. If we run a loop, we would only need to loop about 70 trillion out of the 246 trillion. So we found basically in the first quarter of numbers. We got lucky. But we're not gonna look through this. We did an analysis, and the analysis said this is the correct value. So our second star for task 17, and I'm gonna let you go. I'm out for a Christmas celebration with some friends, and you can mash the buttons, don't touch the bed button, and keep developing.